Welcome back to Math 103 College Algebra at Central Connecticut State University. In this section, section 2.4 from our text, we're looking at modeling with functions. Basically, what it means in mathematics when we use something, when we call something a model, basically we're going to use an equation. We're going to write an equation to represent what's been happening, and then we can use that equation to predict what will happen in the future. Okay. So there's two characteristics for a model. Okay. It's used to explain present phenomenon. Okay. It should use the data that you have available. You don't get to contradict your data and think, take what you like, ignore what you don't like. So we explain the present phenomena, what's been happening, what we see happening. And then, like I said earlier, we use that to make predictions about the data that we could look into the future to make an estimation of what we expect to happen, or if things continue, this is what we would expect to find. Okay. So primarily in this section, we're going to look at linear models. Okay, we're going to model with linear functions. So our functions, f of x equals mx plus b, we're going to have a linear function. Okay, remember that b is often called a y-intercept, or better, it's called an initial value, the amount that you begin with. So the initial amount or the initial value. M, which is normally called slope, referred to slope, it's actually rate of change. So we have a constant rate of change. Typically, we see a linear function or linear equation written with f of x equals mx plus b. So that first one would look like f of x equals mx plus b, where the mx comes first. If you prefer, you could write it f of x equals b plus mx. And in my opinion, that doesn't really make that much of a difference. For example, you might be familiar with classic equations that we give students in an algebra class. Let's suppose that you have an account with $50 in it and you add $10 every week. The initial amount is $10, and then you add $10. I'm sorry, by equation, my example was you start with $50, right? So f of x is equal to $50, the initial amount, and then you add $10 every week, where x represents the number of weeks. So if x is 0, after 0 weeks, you have $50. If x is 2, that means that you've added $10 2 weeks, and you would now have $70. So whether you write that function in the form f of x, where y equals mx plus b, or f of x equals b plus mx, it really doesn't make any difference. So let's look at some examples. In 2015, the average cost of attending a public college was $9,400, and it's projected to increase on average by $300 per year. If I'm going to write a function, here's the first thing I would tell you to think about. We don't think of years as being a time measurement, but it is. So in this case, and I'll try to write this so that you can read it, we're going to let x represent the number of years since 2015. So in the year 2020, I would not use 2020 to represent the year 2020. I would let x be 5 in the year 2020. X would be 0 in the year 2015, and so on. So if I allow that to happen, then f of x, the cost of attending college as a function of x, the number of years since 2015, okay? 2015 is the initial year. In that year, the cost was $9,400. So we're going to say that the initial cost is $9,400. College is, in this example, projected to increase $300 per year. And so there is the formula that I would use to model that situation. If, like I said, I wanted to estimate, so let's just say in 2025, x would equal 10, because 2025 is 10 years after 2015. So f of 10 would be 9,400 plus 300 times 10, or 9,400 plus 3,000. Based on that estimate, I would expect that college would cost $12,400. Okay. Let's go number 2. A car's speed is 50 miles per hour, and it begins to slow down at a constant rate of 10 miles per hour for each second. So x will represent the number of seconds that the car is slowing down. F of x will represent the speed of the car after x seconds. The initial speed is 50. The car is going to slow down. In other words, its speed is going to decrease at 10 miles per hour for each second. There's our function. Okay. In a little bit, we'll have a conversation about domain and range. So for example, in number 1, x is going to increase. We could look at 2015, 2018, 2025, and project that into the future. Number 2, there's a limit to how many seconds it will take for that car to slow down, right? X could be 5, where it will take 5 minutes for the car to reach 0 miles per hour, but x can't be greater than 5 because a car can't go negative miles per hour. Page 2. Very similar, we just have a few more questions. A 100-gallon tank, initially full of water, is being drained at a rate of 5 gallons per minute. So the first thing we want to do is write a formula for a linear function that models the number of gallons of water in the tank after x minutes. Following our pattern from earlier, f of x represents how much water is in the tank. There is initially 100 gallons, and the water is going to be drained, or the amount of water is going to decrease 5 gallons per minute, where x represents the number of minutes. Okay. So again, let's suppose we say that f of x is equal to 100 minus 5x. How much water is in the tank after 4 minutes? What happens there is we replace the x with 4 because we're draining water off for 4 minutes. So f of 4 will equal to 100 gallons minus 5 gallons per minute for 4 minutes. 5 times 4 is 20. So we've released 20 gallons from the tank. So f of 4 will equal 100 minus 20, which is 80. After 4 minutes, there's 80 gallons in the tank. Now, C is a little bit trickier. Identify the x and the y intercepts. Let's talk about the y-intercept first. The y-intercept is when x equals 0. So I would say f of 0 equals 100 minus 5 times 0. That equals 100. What you'll notice is that the y-intercept is the initial value. So to interpret the y-intercept, initially, there are 100 gallons in the tank. For the x-intercept, that's when we let y equal 0, or f of x equals 0. And I'm going to do that work over here on the side. F of x equals 0 when we have the x-intercept. So in other words, that 100 minus 5x will equal 0. If I add 5x to both sides, 5x equals 100, divide both sides by 5, x equals 20. My x-intercept is the point 20, 0, right? My y-intercept was the point 0, 100, meaning after 0 minutes, there's still 100 gallons in the tank. The x-intercept, 20, 0, means that after 20 minutes, there's 0 gallons of water left in the tank. So the y-intercept will tell me how much, or what the initial value is, how much water is initially in the tank. The x-intercept tells me how long it takes for the tank to be empty. Looking at D, then, that leads us into the discussion of domain and range. The domain is the x values. So the domain is the set of x values such that x is between 0 and 20, because you're going to be draining water off from 0 to 20 minutes. You can leave the spigot or the faucet open on the tank after 20 minutes, but there's no water to come out. So the whole situation ends after 20 minutes. Your range is your set of Y values. Y is somewhere between 0 and 100 gallons. Notice we still list them from least to greatest. So you're going to start with 100 gallons and drop to 0 gallons. The amount of water that's in the tank is always going to be somewhere between 0 and 100 gallons. Okay. So let's look at another example here. A roof has half an inch of layer of ice on it from a previous storm. Another ice storm begins to deposit ice at a rate of 0.2 inches per hour. Find the linear function. I'm going to start this the same way, where the initial amount of ice, where did we go? The initial amount of ice on the roof is half of an inch. Didn't get cleared off after the previous storm. So now we have another storm coming in, and ice is accumulating on the roof at a rate of 0.2 inches per hour. Okay. Things here are going to work very similar as to above. How thick is the ice after 2.5 hours? Again, I'm going to replace the x with 2.5 on both sides of the equation. Okay. So 0.5 plus 0.2 times 2.5 is 0.5, right? So that means that we should have 1 inch after 2.5 hours. Okay. At this rate, how long would it take for the ice to reach 3 inches? You got to be careful of ice on your roof. Maybe you know engineering, if once that ice reaches 3 inches, you're going to have a problem. How long will that go? Well, in that case, I wonder when f of x will equal 3 inches. When will 0.5 plus 0.2x equal 3? So I'm going to subtract 0.5. Forgive me again. Subtract 0.5 from both sides. 0.2x equals 2.5. I'm going to divide both sides by 0.2, and x should equal 12.5. Verify that with a calculator. The way I'm doing that is I'm multiplying top and bottom both by 10. That's the same as 25 over 2, which should be 12.5. Now 12.5 what? X represents time in hours. So 12.5 hours is how long it will take for the ice to reach 3 inches. Okay. Now let's take a minute and look at another type of a function here called a piecewise function. I think of going to a parking garage. You know, the first hour costs 75 minutes and each additional hour costs $1. Or, you know, and when you do that, things change. So not all units of time are the same scenario or the same situation. Okay. So what you'll notice here in example 5 is for 4 years, over several years, Gallup surveyed people asking whether they thought the current time would be a good time to change jobs. So in the 4 years from 2003 to 2007, the percentage of people who agreed that it was a good time to change jobs went from 21 to 43%. But that you'll notice in the next 2 years, that percentage dropped from 43 to 10. And in the next 6 years, from 2009 to 2015, the percentage went from 10 back up to 42. Okay. Now, the first thing I'm going to do here is I'm going to change my years. I alluded to this earlier when we looked at 2015 and the number of years that the cost of college has been increasing since 2015. I'm going to let X here represent the number of years since 2000. So the year 2003, I'm going to call it 3. 2007 is 7. 2009 is 9. 2015 is 15. The reason I want to do that is to get a visual representation of what's happening. Let's suppose that we did a rough sketch. It's 5, 10, 15, 10, 20, 30, 40%. If I plot these points, 321 is right about here. 743 is way up here. So we can see the increase like this from 2003 to 2007. However, the 0.910 is way back down here, so that percentage dropped. And at 2015, we're back up to 42%, so that's about here. And so this went back up. So I've got three different pieces to this function. If I want to find, and I'm going to use different colors here, if I want to find the equation of this line, that line goes from the point 321 to the point 743. So if I find my slope, 43 minus 21 over 7 minus 3, that's 22 over 4. I'm going to call it 11 halves. If I say y equals mx plus b, if x is 3, y is 21, so we have 21 equals 11 halves times 3. We're going to get into some fractions here. And so we have 21, which we're going to call 42 halves, equals 33 halves plus b. So b, when I subtract the 33 halves from both sides, b is 9 halves. So this equation is f of x equals 11 halves x plus 9 halves. The equation is going to be different for the other two. Okay. You take a minute and see if you can find the other two equations. To go from 743 to 910, my slope is 10 minus 43 over 9 minus 7, so that's negative 33, oops. Negative 33 halves. So I'm going to pick my y. What do I want to use? Let's use 43 and 7. So 43 equals negative 33 halves times 7 plus b. I'm going to roll over to my desk now and get a calculator, I think. So 43 is 86 halves. And 33 times 7 is 231. So this is a negative 231 halves plus b. When I add, I'm going to push this up just a little bit. When I add the 231 halves, we have 86 plus 231 halves. We're going to get 317. This is pretty ugly. 317 halves. So this equation is y equals negative 33 halves x plus 317 halves. Okay, one more to go. This is not always fun. We got one more to go. We use this bright green. For this piece, we're going to go from 910 to 1542. So that slope is 42 minus 10 over 15 minus 9, or 32 over 6, which is equal to 16 thirds. So y, I'm going to use 10, equals 16 thirds times 9 plus b. Now 9 divided by 3 is 3, so that's nice. So 10 equals 16 thirds times 9. And we should get 48 plus b. So b is a negative 38. So this third equation is y equals 16 thirds x minus 38. So notice we have three different pieces going on. The way that we would write this as a function, we'd call it a piecewise function, is we would say f of x is equal to these three pieces. We're going to use the 11 halves x plus 9 halves when x is between 3 and 7. We're going to use the negative 33 halves x plus 317 halves when x is between 7 and 9. We're going to use 16 thirds x minus 38 when x is between 9 and 15, because this function has three different pieces, and that's called a piecewise function. They can get messy, but really all it is tedious more than difficult, because you're doing the same thing, you just have to do it repeatedly. In B, it says to use that formula to estimate the percentage of people in 2012 that thought that now was a good time to change jobs. What I'm going to do for that is say 12. In 2012, x would equal 12. Which piece of this function am I going to use? I'm going to use the third piece of this function for this part, because we use that third part when x is between 9 and 15. 12 is between 9 and 15. So what we would do to find that is we would say, okay, f of 12 would equal 16 thirds times 12 minus 38. Notice I'm only using that third piece of the function because that's the piece of the function to use when x is between 9 and 15. So we have 16 thirds times 12. That should be 64. Let me double check that with the calculator. 16 thirds times 12 is 64. So we have 64 minus 38. And that would give us 26. So I would predict that f of 12 equals 26, or that in 2012, 26% of the people thought it was a good time to change jobs. Okay. Like I said, it can get involved. It's more tedious than difficult because of the repetition more than anything else. So let's just suppose that we're looking at a piecewise function that we were given, number 6. We have two pieces of the function. F of x equals negative 2x minus 3, and f of x equals x plus 5. You never use both pieces of the function at the same time. We're going to use the negative 2x minus 3 for values of x less than or equal to 1, and we use x plus 5 if x is greater than 1. So first off, we want to look at f of 0, f of 1, f of negative 3, and f of 5. To do f of 0, we say, is 0 less than 1 or greater than 1? 0 is less than 1, so we use the negative 2x minus 3. F of 0 is negative 3. F of 1, well, notice 1 is the boundary point between the two pieces. But because x is 1, we use the top piece if x is less than or equal to 1. So f of 1 is simply negative 2 times 1 minus 3, or negative 5. F of negative 3, again, negative 3 is less than 1. So once again, we're going to use just the top piece. Negative 2 times negative 3 is 6, minus 3 is 3. So you might be asking, when do we ever use the other piece of the function? Well, notice that f of 5, to do f of 5 is greater than 1. So now we're going to use the bottom piece of the function. F of 5 is 10. Okay. For sketching a piecewise function, and this one's a lot easier to sketch than the one in the previous example, but here's what I do. Okay. And I hope you're good with open circles and closed circles and that sort of thing. X is 1, 2, 3. What I'm going to do to graph this is a little bit different than maybe you've seen graphing functions before. I've not labeled all those tick marks yet, but I'll take care of that in a little bit. 1. If x is 1, well, we know f of 1 is -5. So we've got 1, -5, and we're going to plot that. 1, -5. Now I'm going to pick another value of x less than 1. Actually, no, let's pick 1. If I put 1 in the top equation, I get -5. If I put 1 in the bottom equation, I would get 6. 1 plus 5 is 6. And that would be way up here. Except that we can't have a closed circle down here and a closed circle up here. This is going to be an open circle. Because that bottom part of the function is going to come up to the 1 but not quite touch it. So we have an open circle. Now really all I need to do is pick another value of x greater than 1 and another value of x less than 1. If I pick another value of x less than 1, like f of 0 was -3, so there's my point 0, -3. So this, whoops, I'm sorry, that's not 0, -3. That's 0, +3. 0, -3 is down here. So now I know that that is what the top part of the function looks like. Okay. This piece of the function is that arrow. And notice it's only moving to the left because it's values of x less than 1. I've got my open circle here at 1, 6. If I put 2 in, f of 2 would be 2, 7. And that point would look like this. And so that function is going to go from the open circle and up to the right. Okay, so the bottom part of the graph is that function. Notice that these are both the red and the green are both linear functions, but they're two different lines and just pieces of each of those. I hope this makes some sense. Contact me if you want more examples. Maybe I'll do a whole video just on piecewise functions that will hopefully make more sense. Let's look at the last thing I want to talk about here called the greatest integer function. This is sometimes called a rounding down function, or sometimes it's called a floor function. And people get confused when we talk about greatest integer. Why would that be rounding down? The greatest integer function, which has this double bracket on either side of the x, it's the greatest integer less than or equal to x. In examples like a, b, and c here, it's no big deal because what's the greatest integer less than or equal to 0? F of 0 would equal 0. F of -3 would equal -3. F of 2 would equal 2. It seems a little boring and counterintuitive. But look at f of 6.3. If I have f of x equals the greatest function, or the greatest integer, less than or equal to x, f of 6.3 is the greatest integer less than or equal to 6.3. If you think about a number line, let's just say here's 6 and here's 7. Those are integers. 6.3 is in between. If I move to the left, what's the greatest integer less than 6.3? It would be 6. What's the greatest integer less than or equal to 2.9? That would be 2. Notice though, I'm not just dropping the decimal. I'm rounding down. I'm moving to the left on the number line to the next integer less than that value. So let's think about f of -5.5. What's the greatest integer less than or equal to -5.5? Remember, the next integer less than -5 is -6. If -5.5 is between them, that's a pretty ugly 5.5. Let me fix that. If negative 5.5 is between them, and I move to the left looking for the next integer, that's going to be negative 6. The greatest integer less than or equal to negative 5.5 is actually the negative 6. Again, I hope that makes some sense. That is section 2.4 for this class. Again, if you're finding these videos helpful, it'd be great if you would like them. Better yet, subscribe. And I look forward to seeing you next time.